Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next several weeks, I will be releasing sample free response questions from each of the 4 AP Physics exams to help students familiarize themselves with what kinds of questions will be asked and how the AP Physics exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day, and this video series is intended primarily to help those students. According to AP Central, the AP Physics 2 exam contains 1 experimental design question, 1 qualitative to quantitative translation question, 1 paragraph length response or paragraph argument question, and 1 short answer question. And the question in this video is type number 3, a paragraph argument or paragraph length response. We'll be looking at AP Physics 2 2016 question number 4, which covered DC circuits and capacitors. Some students are investigating the behavior of a circuit with 4 components in series: a resistor of resistance R, a capacitor of capacitance C, a battery with potential difference E, and a switch. Initially, the capacitor is uncharged and the switch is open. Part 1, determine the current in the resistor and the potential difference across the capacitor immediately after the switch is closed. So, because there's no charge on the capacitor, there's no potential difference across it. Therefore, the entire battery potential is across the resistor, so the current is that potential divided by the resistance. So note that we don't actually have to give any explanation here. We just need to indicate, oops, let me erase. We just need to indicate that the current is equal to the EMF divided by the resistance, and the voltage across the capacitor is 0, and right there is our point. Part 2, determine the current in the resistor and the potential difference across the capacitor a long time after the switch is closed. So once the capacitor is fully charged, it allows no current to pass. And because all the components are in series, there's no current at all in the circuit. And with no current, there's no potential difference across the resistor, so the entire battery potential is across the capacitor. So we simply need to state that the current equals 0 after a long time, and the voltage across the capacitor is equal to the EMF, this curly E. And right there is our point. +1 for indicating that I equals 0. And the voltage on the capacitor is equal to the EMF. Part B, the switch is open, the capacitor is discharged, and a second identical capacitor is added to the circuit in series with the other components. The switch is then closed again. Part 1, a long time after the switch is closed, the energy stored in the single capacitor in the original circuit is U1, and the total energy stored in the 2 capacitors in the new circuit is U2. Calculate the ratio U1 to U2. So let me grab my pen tool. So the energy 1, U1, is going to be 1/2 times the capacitance times E squared. And then we have 2 things that we could think about for U2. First of all, we could think about the fact that with the capacitors being in series, they will each have half the voltage of the original capacitor. So the total energy will be 2 times 1/2 C times E divided by 2 quantity squared, because of course 1/2 C times E divided by 2 quantity squared is the energy on a single capacitor, and we can just add them. Or we can think about the fact that the equivalent capacitance is going to be half of the original capacitance for our capacitors in series. So I could just do 1/2 C over 2 for the equivalent capacitance times E squared. And either way we think about this, we're going to get 1/4 C times E squared. So then when we calculate the ratio of U1 to U2, we will have 1/2 C E squared divided by 1/4 CE squared, and that gives us a ratio of 2. And for scoring, we're going to get 1 point for a calculation that shows, or that indicates, one of these two things that I pointed out for you too. And rather than write them out, I'm just going to underline here. We're going to indicate that V2, the voltage across one of the new capacitors, is equal to half the voltage of the original, which of course, but we're using the symbol E. So why don't I really actually just fix that whole little thing there? We're going to write this as, so we're going to point out that E2 is equal to half of E1. Or we're going to point out that the equivalent capacitance of the new circuit is half of the capacitance in the original circuit. And then our second point comes from correctly calculating the ratio. Part 2. The two capacitors in series are to be replaced with a single capacitor that will have the same energy U2. Indicate a plate area and a distance between the plates for the new capacitor compared with one of the original capacitors that will accomplish this. Support your reasoning using appropriate physics principles and/or mathematical models. So the energy stored equals 1/2 capacitance times the voltage squared. The potential difference across each of the single capacitors is the same. And for the energy stored in the single new capacitor to be half that of the original single capacitor, the new capacitor must have half the capacitance. Capacitance equals epsilon naught A divided by D, so half the plate area with the same distance between the plates, or twice the distance with the same plate area, will accomplish this. And so a point was awarded for any combination of area and spacing that is consistent with the student's answer for the ratio in Part B1 with the proper principle or model as support. Students are then asked to design two circuits, each containing a switch, a battery with a small internal resistance, a light bulb, and a capacitor. In arrangement 1, the bulb should gradually light up after the switch is closed, becoming brightest after the switch has been closed a long time. In arrangement 2, the bulb should be brightest when the switch is first closed, getting dimmer with time, and going out completely when the switch has been closed for a long time. So part C, using standard circuit symbols, draw two circuit diagrams, one showing a possible circuit for arrangement 1, and the other showing a possible circuit for arrangement 2. Justify your circuit diagrams with a paragraph-length explanation referring to the properties of light bulbs and capacitors in circuits and the conservation of energy and/or the conservation of charge. So, arrangement 1 is going to have the bulb and the capacitor in parallel, and arrangement 2 is going to have them in series. So the bulb will be brightest when the current through it is its largest. The capacitor acts over time to stop the current from flowing as its voltage approaches that of the battery. So to have a bulb that is initially dim and gets brighter over time, as in arrangement 1, the bulb and the capacitor need to be in parallel. The capacitor initially acts like a wire while its voltage is very low, so more of the current flows through that branch, leaving the bulb dim. As the capacitor's voltage grows, less current flows through that branch, and more will flow through the bulb, making it grow brighter over time. And when the capacitor's voltage equals that of the battery, all the current will flow through the bulb. For arrangement 2, to have a bulb that is brightest when the switch is first closed and gets dimmer over time, the bulb and capacitor need to be in series. The capacitor initially acts like a wire while its voltage is very low, and the bulb has the same voltage as the battery, so current flows easily and the bulb is very bright. As the capacitor's voltage grows during charging, it pushes back against the battery and less voltage is left for the bulb, so less current flows and the bulb gets dimmer over time. Once the capacitor's voltage is equal to that of the battery, no current flows and the bulb goes out. So the scoring for this was a little bit complicated because you could talk about conservation of charge or energy. So there are 3 points that are going to exist regardless of the route that you chose. We'll talk about those first. 1 point will be for 2 correct circuit diagrams, each matched with the correct situation. Arrangement 1 has the light bulb and capacitor in parallel, and arrangement 2 has them in series. 1 of the points will be for indicating that the light bulb is brightest when the current through it is maximum, and the capacitor eventually stops current from flowing in its branch when the potential difference across its plates is equal in magnitude to the EMF of the battery, or something similar to this. And then the final point that's the same regardless of whether you talked about conservation of charge or conservation of energy, final point is for a response that has sufficient paragraph structure as described in the published requirements for the paragraph length response. So the final 2 points involved discussing your response using current, conservation of charge, or using potential difference, which was conservation of energy. So if you responded using current, your point would be for indicating that in the series circuit, where the same current flows through both components, the most current flows right after the switch is closed and decreases as the capacitor charges. Your second point would be for indicating that in the parallel circuit, where the current is shared between the components, the most current flows through the light bulb a long time after the switch is closed, because the full current initially goes through the capacitor branch because it acts like a wire with very low potential difference, then ends up all through the light bulb once the fully charged capacitor acts like an open circuit and has the same potential difference as the battery. If you discussed your response using conservation of energy using potential difference, your first point would be for indicating that in the series circuit where the potential is shared, the resistor has its maximum potential difference right after the switch is closed because the capacitor starts out uncharged with no potential difference and then charges until it has the same potential as the battery. Your second point would be for indicating that in a parallel circuit where both components have the same potential difference, the bulb starts out with the same zero potential difference as the capacitor and ends up with the total battery potential. I hope you have found this explanation of a paragraph-length response for AP Physics 2 helpful. If you have a video solution request for my YouTube channel, you can send it to physicsproblemrequest@gmail.com, but I won't be putting up any additional videos until the AP Physics series is concluded. If you need some email assistance, you can send your question and the work you've done on it so far to freephysicshelpline@gmail.com with a limit of 10 questions per academic year. If you'd like to learn more about my online physics tutoring services, you can reach me at brandyhevlinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics 2 exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.